Okay, good evening. This is Professor David J. Delosreyes. Okay, my discussion for tonight will be a long video format discussion, and this will be on the topic alternating current machines. And we are now on lesson number 14. Okay, we are now on lesson number 14. So let's continue alternating current machines. Lesson number 14. The title of the topic is transformer percent regulation. The computation of how reliable the voltage of a transformer is. Okay, let's proceed. The title of the topic for tonight will be Alternating Current Machines, lesson number 14. We are running smooth. Okay, transformer percent regulation. By definition, the so-called percent regulation, this deals with the so-called how reliable how reliable are the voltage given by transformers going to our service entrance, meaning the voltage coming to our homes. Like in here, the voltage or the specification of the transformer supplying our houses is 240 volts. So meaning to say this 240 volts is actually the full load voltage, because at no load this 240 is not actually 240, it should be higher. Because when our homes consumes current, okay, there will be a voltage drop. So actually, the voltage, actually the given value 240 is actually higher than 240. It is supposed to be higher than 240. Then at full load, it will reduce down to exactly what will be the specification written on the transformer. It's 240. So if it could maintain that value 240 at full load, okay, that transformer is actually very reliable, meaning the transformer losses are actually not affecting the so-called reliability of the voltage, because the copper the lamination losses, the losses on the iron core, okay, will have a significant effect on the value of the terminal voltage. Okay, let's proceed with the explanation. This is a little bit storytelling, because AC machines, it's storytelling, right? We are discussing concept and we are discussing equations and how to solve parameters for transformers. Okay, I will try to read what's the definition of a percent regulation. A measure of how well a power system or electrical equipment can maintain a constant voltage under varying load conditions. It determines the reliability of electrical equipment. So, meaning to say, from the definition here, if we try to summarize percent regulation, this is referred to as the so-called reliability test. Right? So if we say percent regulation, it is the so-called reliability test. Percent regulation is actually different from efficiency, because under efficiency, the losses we are considering there is different from the what they call these losses in the computation of the percent regulation. So percent regulation is actually different from efficiency, because in the next discussions, that will be our next topic on how to compute the efficiency of transformer. Okay, there will now be the so-called copper losses, because on the voltage regulation and on the percent regulation, okay, the what you call this, the losses that is only being considered is actually the losses on the lamination, right? Because whether we like it or not, there should be losses on the lamination. How good is it, the lamination? If it is made of steel plates, how good is the steel plates? So, such that the losses will be minimal, right? So if we are only having a steel plate in which the what you call this mixture content maybe is different, okay, it's an ordinary one, the losses might be high. So if the losses is high, of course, the percent regulation is high. So to maintain a low percent regulation, the material things, okay, that is being used for the lamination of the transformer, the core in which the windings are worn, okay, it should be a good lamination. Okay, let's proceed. Since we now know the definition of the regulation, percent regulation in just summary is just actually the so-called reliability test, meaning if this is 2400 and this is 240, this is now the transformer, right? If the voltage going to our houses is 240, this 240 here is actually the voltage at full load condition. And this 2400 is also at full load. Because if this is no load, when current is coming out on the secondary, of course there will be losses, right? So this 240 will not be maybe 240, it will become 235 or 230. So if your equipment is using or might be using a 240, there will be a problem with that machine. So actually it is a must that utility companies should maintain a good percent regulation. So I am telling you now, this 240 volts on the given example is actually full load value. Full load. And this 2400 on the primary side is also the full load value. Okay, so in the computation of the so-called percent regulation, we will be needing a value which is greater than this full load value. Because full load, there are some losses already, so there should be a no load value. So the no load value, for us to maintain a 240, we should have a no load voltage of maybe around 245. Right? So when current is coming out of the secondary, there will be losses. Okay? And that losses may be due to this 5 volts over here. So with that losses, okay, at full load, okay, it will maintain 240. Because if you could not, produce a 245, of course, when current is going out, it will become lesser, right? So if there is no 45 but no load, what comes out at full load should be less than 240, right? So utility companies are actually graded on how reliable their systems are. And how reliable is it? They should be using good transformers, meaning the laminations that is being used in which the windings are run should be a good one, you know. The quality of the materials for the lamination should be a good one, okay? Plus the wiring you could not do about it because if it is number 8, it's number 8. There is a certain resistance for that. If it's a number 4, the resistance will be different. So meaning to say, if you are using a higher rating wiring, of course the resistance will be lesser. But if you are using a very thin wire, of course the resistance will be big and the voltage drop will be big. Okay? So in the winding portion, they should be using a high capacity wiring to minimize the so-called IR drops, the voltage drop due to the resistance of the wiring. Okay? So, if we now try to bring out the formula on how to compute percent regulation, for a transformer percent regulation, this is different from efficiency. It should be capital letter B with the subscript and L, meaning the voltage at no load, and minus capital letter B with the subscript and L, not first lady, it's full load, all over B with the full load subscript times 100%. Right? This full load values is actually on the secondary side, this is 240. Okay? On the primary side, it is 2400 for a step down transformer, right? And this, the one we are to compute for the percent regulation should be the voltage at no load. we should be computing a value greater than 240 and 2400. Why? Because there are IR drops, right? The voltage drop. Whether we like it or not, there should be a voltage drop due to the resistance of the winding and due to the reactance of the winding. Right? Okay, I will try to erase this one now so it will look good. Okay, I will rewrite this one. It should be voltage at no load minus voltage at full load all over voltage at full load times 100%. Okay, so this will be the formula on how to compute for the percent regulation of transformer. Okay, it will be the voltage at no load minus the voltage at full load over voltage at full load times 100%. And we are talking terminal voltage here, terminal. What terminal? It is the voltage across the secondary, am I on the camera? Secondary and the primary. So we are talking terminal voltage there. It's not the induced voltage, right? Okay, let's continue. To visualize the concept on how to compute percent regulation, let's try to bring out an example problem. Okay, the example problem, actually this will now be example number 3. Because from the previous lesson, 13, I've given you a continuity problem, example number 1 and number 2, in which the unknowns for example number 1 and number 2 is a continuous thing. So actually this example number 3 emanates from example number 1 and number 2. So we will be using the data on example number 1 and number 2 to compute what is being asked over here. Okay, so I don't need to rewrite the given equation. For those who are following my channel, you should proceed to lesson number 13 before you go to lesson number 14. I will try to read the example number 3. Using the data of example number 1 and number 2 from lesson 13, calculate the percent regulation at unity power factor. There is a load here. Okay. And the power factor is unity. It is equal to 1. The significance of this power factor equal to 1 is that the secondary voltage is in phase with the current. From our vector diagrams, right? If this is the voltage, the current is isobase for power factor equal to unity or 1. This is the voltage, it has 0. So the power factor is unity. Of course, the current should be in phase. Okay, when the voltage goes up, the current should goes up also and goes down. They are in phase, right? Okay, let's bring out what is given. From example number 2, because we have to compute for the percent regulation, we need the vector diagram for the voltages, okay? So using primary values, I forgot to underline this one. Using primary values. Because we will be presenting 2 solutions, and these 2 solutions will bring out 2 same answers. So in your exams, okay, you could either use the primary values or secondary values. It depends on what is given. But from example number 1 and number 2, we are given the primary and secondary values. So on example number 3, we will be using the primary values and we will be using the secondary values, and supposed to be what will come out will be the same. Okay? So from example number 2, the primary values. Primary values meaning the voltage drops we have computed. Right? The voltage drop due to the resistance equivalent is at 33.3 volts. And the voltage drop due to the reactance, okay, is 58.33. This is I also open quantity. What's the significance of this one? This one got a, what do you call this? These two here got a vector diagram, right? The first IARI, the product IR is this one. The product IX will be this one, right? This is IR. This is IX. This is equivalent already, right? We are considering these voltages. We are to add these two voltages here to the given terminal voltages to compensate for the value as it comes out. Okay, so if we try to place the other voltage here, if we are considering primary, this should be BP, right? And the vector sum of BP plus IRA vectorially with IXE actually represent the so-called voltage at no load. Right? The voltage at no load is actually greater than the voltage at full load due to this IR drop and IX drop. Okay, and the simplified value of this, if we try to use the primary values, it is this. Right? For us to get a 2400 here, we must have to generate or produce a voltage greater than 2400. And that increase in value is actually coming out from the IR drop and IX drop. Right? Since we are now given the IR drop on the primary, IX drop on the primary, we draw the vector diagram, it is this, or it is actually this one. Right? This is the IR drop. This is the IX drop. This is the original terminal voltage at full load. So to get this 2400, we must have to add this 33.3 vectorially with this to get a total value of 2434. Right? We must have the utility company must have to produce 2434. So when it arrives at the terminal of the primary of the transformer, it will come out as 2400. Right? Because if it's less than 2400, the specification given on the transformer is wrong, right? It's not reliable. Their transformer is not reliable. So actually, they must have to produce 2434. For the voltage that will arrive here will be 2400. Right? So using the second primary values now, this is 33.3, this is 2400, this is the IX drop, it's going up, right? 2400 is actually at 0 degree, the IR drop is actually at 0 degree, so we add this one here, 2400 plus 33.3, it is this. Right? That's the real part of the voltage. And the imaginary part, it is due to the reactance of the winding, it is this, 58.33. Right? So we are actually using Pythagoras principle here. We are given this side, so we could compute for the hypotenuse, which represents the voltage of the primary at no load. We are on the primary values, right? So this is B with the subscript B, again with the subscript NL, meaning no load. So if we try to compute this one, simplify. You square this one, you square this one, you add it, it is approximately the square root of 5.92 times 10 to the 6, and what will come out will be 2434. Okay? So meaning to say, if you want a 2400 here, prior to that, you must have to produce 2434 due to the voltage drop on the transformer. Right? Okay? There should be a 2434. So actually, there is an increase. You must have to produce 34 volts more, 34. Okay, so when it passes through the IR drop and IX drop, it will come out as 2400. Oh, that's the meaning of that one. Okay, I will try to erase this one so it's not wrong. So if we now try to simply compute this one, okay, the primary voltage at no load as per computation is 2434 due to the IR drop and IX drop, and the voltage of the primary at full load, it's the given value 2400. So percent regulation now will be no load minus full load over full load. 2434 minus 2400 over 2400 times 100%. And this is 1.417%. This is very good, right? Why it's very good? It's not an efficiency, meaning how reliable it is. Meaning to say, you apply a certain voltage and it will just adjust a little bit below what they call this 1.417%. So it's reliable, right? This is not efficiency, it's the so-called reliability of the voltage. You produce 2400 or 2434, after passing the IR drop and IX drop, it will become 2400. So that was a very nice thing because as per computation, what comes out is only 1.417%. Okay? Oh, that's the primary solution. For the secondary solution, it's the same. It's just that the values were actually divided by the ratio transformation. So using the secondary values, this portion here is not 2400. It should be 2400 divided by the ratio transformation times. This is actually 240. Because our transformer was got a rating of 2400 over 240. Okay, so we are now on the secondary side. So on the secondary side, this is 240, and the IR drop due to the resistance is 3.33. So this is 3.33, right? And the drop due to the reactance referred to the secondary, of course, referred to the secondary. We are done with the primary. It is 5.83. So if we try to take the vectorial sum of this, 240 plus 33, they are the same, both real parts. So this is 243.33, the sum. And the imaginary part is 5.83, the up portion. 5.83 square. Taking the sum of the squares, it will be 59,243.47. Taking the square root, it's approximately 243.4 volts. Okay? So, meaning to say, we must have to produce 243.4 volts at no load. Okay? So, at full load, you could get out 240 volts, right? There is a voltage difference of around 3.4 volts referred to the secondary. You got what I mean? You must have to produce a 243.4 at the secondary at no load. So when the full load condition appears, right, it will drop to a value of 240 exactly. So if we try to compute the regulation, it should be the same. It should be 243.4 minus 240 over 240, and the result is the same as 1.417%. Okay, that's a percent regulation of transformer. Okay? Percent regulation is actually how reliable the arriving voltage at our terminals. Okay? At no load, the terminal voltage should be high. Okay? If you got two lines here, at no load, of course, supposed to be the voltage here should be high. As soon as we connect the load, whether we like it or not, the voltage will drop. Okay? So the voltage at no load minus the voltage at full load over the voltage at full load represents the percent regulation of how reliable are actually the terminal voltage that is arriving at our terminals. Right? Oh, that's a percent regulation of transformers. Okay, this is Professor David J. De Los Reyes. Good morning from Los Angeles.